Welcome to Astrum Space and Galaxy, your gateway to the wonders of the universe.
There's a star within our galaxy that doesn't act like any of the others. It doesn't glow the brightest, or burn the hottest, or even rest quietly in some predictable corner of the evening sky. Instead, it rotates so quickly it makes jet engines. Looks slow, and it is so dense that a teaspoon of its substance would weigh more than a mountain. But that's not the frightening part. The actual issue is that this entity is unstable. It's on the brink. One false move, a little more mass, a little more pressure, and it travails up into something even more sinister. A black hole. And the thing is, this isn't some far-off object on the fringe of the observable universe. It's in our galaxitote, rotating, consuming, expanding. Scientists have been aware of it for a while. They even named it. But despite all the information we've compiled, there's one thing they still can't answer. When is it going to explode? Perhaps the real question is, are we certain it hasn't already? Meet the Pulsar. The galaxy's cosmic engine of doom. When a star finishes its life cycle, it doesn't go quietly. It burns all that it has in an attempt to resist off the inevitable gravity. And once its nuclear fuel runs out, gravity wins. The core collapses. The outer layers explode in a supernova. What's left behind is something strange, something small, something impossibly heavy. What you get is a neutron star. It's not just dead, it's transformed. Now, a typical neutron star isn't much bigger than a city, be 20 kilometers across. You could drive over it in less than half an hour if you could somehow. Land on it without getting crushed or incinerated. Butte in that little volume, it's got more mass than our sun. It's like cramming every human, planet, mountain, and ocean of 4 solar system into a Manhattan-sized sphere. Now it gets crazy. Because it's so compact, a neutron star has insane density. 1 teaspoon of this stuff would weigh over 1 billion tons. That's more than the weight of every building in New York City combined. If you dropped a piece the size of a sugar cube onto Earth, it wouldn't just sit there. It would punch straight through the crust, rip through the mantle, and continue on until it struck the core. It wouldn't even lose speed. But that's just start. Some neutron stars rotate, not merely slow-moving like Earth. They rotate quickly. So quickly that they flash bursts of radiation through space. Like the rotating beam on a lighthouse. That's what we call a pulsar. Not because it pulses like a heartbeat, but because those beams sweep past us at regular intervals, and they look like pulses when we detect them. At first, scientists had no idea what they were. Back in 1967, when Jocelyn Bell first picked up the rhythmic signals of the first known pulsar, the team didn't rule out aliens. That's how strange it was. Something in outer space was broadcasting radio pulses with the regularity of an atomic clock. Eventually, Y identified it. It wasn't ET. Something far more strange. His objects rotate at 100 soft revolutions per second. That's quicker than helicopter blades, quicker than your kitchen blender, and in some instances, even quicker than a jet turbine. They're cosmic flywheels that are 100 Schumann machinery, both in speed and in endurance, and they don't let up readily. Most OFMs have been spinning like this for millions of years. Pulsars sustain these speeds for millions of years because of their huge angular momentum and minimal energy loss. And here's where it gets risky. Some pulsars don't live alone in emptiness. They get companions, not by their own volition, but because they have Tobia mechanism known as accretion. It can maintain them spinning very fast for incredibly long times. Stars near air trapped in their gravitational hold. Eventually, the pulsar accumulates enough material from these tragic companions. The doomed companion, typically a low-mass star, is deprived of its outer regions. Its matter ripped away in a blistering stream of superheated plasma. This spinning deluge of gas pours into the pulsar, bringing a blast of energy. It rotates faster. It accumulates mass. It gets more intense. Scientists refer to these black widow pulsars, much like Thespeter. They kill their mate after copulation. Only in this case, the pulsar does not merely annihilate its partner, it divorces finitely small pieces of it atom by atom. This does not continue indefinitely. There is a point at which mass a neutron star can contain. And after it goes past that threshold, the structure no longer holds. The neutron pressure collapses. Gravity asserts itself, and the pulsar crashes again, this time as a black hole. So when we tell you some of these stars are dangerous, it's not because they're going to explode and transmit shockwaves across the galaxy like a supernova. It's because they're already beyond ordinary stars. They're dense, mighty, rotating bombs, waiting to go off, and the one we're looking at isn't an ordinary pulsar. It's the most rapidly rotating, most massive neutron star yet discovered, and it's resident there in our own galactic backyard. Let me show you why this one is different. This one is different. The galactic Reaper not. All pulses are created equal. The majority of them rotate rapidly. Most of them are dense and mighty, yes? But occasionally, astronomers encounter something that doesn't merely conform to the definition. It redefines it. One such is PSR J09520607. It doesn't have a flashy title, nor does it appear in a sci-fi film. What it does possess is a resume that looks like a warning label from the universe itself. This thing is spinning, 707 revolutions per second. That is not a typographical error. It spins more than 700 complete revolutions every second. You couldn't even blink that quickly if you tried. It spins so quickly that its surface is traveling at a large portion of the speed of light. And yet, it isn't blowing itself to gravity keeps it bound together, compressing it so hard that even the atoms themselves longer exist on the surface. The only stuff remaining is neutron matter, packed so tightly, electrons and protons have combined. And to top it off, it's the most massive neutron star ever found. Close to 2.4 times more massive than the Sun, all packed into a diameter of just 20 kilometers. That combination, super spin, and almost critical mass is why this object issues artists. Because here's the twist. Neutron stars aren't even meant to be Chevy. It's the maximum. The so-called Tolman-Oppenheimer-Volv limit is about 2.5 to 3 solar masses. Past that, the neutron pressure can't hold up against gravity anymore. Star collapses into a black hole. So, this one, it's close. It's really close. And we now know how it got this way. It wasn't born this massive. It ate its way here. Orbiting this pulsar is dim, fading remnant of a star, a white dwarf that's being slowly like a drop of water falling into a drain. Its matter spirals toward the pulsar. Some of it accretes. Some of it is a hot, glowing accretion disk. Either scenario, the pulsar is gaining mass. It's also gaining spin, similar to an ice skater bringing arms in. Reducing the radius adds angular momentum. The more it eats, the faster it spins. That's what makes these type systems so extreme. The process doesn't just speed up the pulsar, it stresses it out. Each gram of pilfered material brings it closer to the limit, closer to collapse. Astronomers refer to it as a black Weddell pulsar, and the metaphor is apt. The pulsar sucks dry its companion until it is nothing. The white dwarf dwindles, the pulsar expands, and finally, there is nothing left but one neutron star. Unstable and bloated, waiting for a final push, and that's where it becomes creepy. As opposed to a supernova, which is announced by an explosion that you can see, this collapse would not warn us at all. There'd be no burst of light, no massive shockwave, just an abrupt quiet. The pulses cease. In the quiet, a black hole is formed. We have no idea when that's going to occur. This might be a million years from now, might be tomorrow, might already be done. And we're just waiting for word to travel 14,000 light years to find its way to us, just in case we're not sure. This object is within our own galaxy. It's not some distant oddity in some far-off cluster. This is a ticking time bomb spinning at full throttle right here in the Milky Way, and the only reason it hasn't turned it into a black hole yet is because it's still holding itself together by sheer momentum. Spin is buying it time. But eventually, time runs out. So let's say it happens. Let's say this what happens if it collapses. Pulsar finally crosses the unseen line. It sucks in just enough mass from its companion star. As it's dying and the tenuous balance, keeping it intact shatters. What precisely happens after that? Well, the star doesn't blow up. Not like we're used to thinking about explosions. It collapses quietly immediately. One moment, it's a pulsar, spinning, shining, pulsing like a galactic lithus. The next, it has vanished. The pulses cease. The light disappears. The radio waves we've been receiving from Earth just discontinue. No flash, no sound, just a switch. Flick, and what's left over is a black hole. This is where the actual physics come in. Unlucky supernova, which expels most of the star's mass in a flash of gas and light. Pulsar collapsing into a black hole leaves nothing visible behind. Shell to spit out. The stuff is already packed as tightly as it can be, so the collapse is tidy, direct or efficient. From outside, the object is invisible, but its presence is still there. Space around it curves. Time slows down close to it, and anything close enough drops in. Here's the good news. Even though this may occur tomorrow, we would not feel a thing down here on Earth, at least for some time. This pulsar is roughly 14,000 light years from us. So if it had collapsed today, the impact would not be felt here, for Anathor, 14,000 years. Technically, it could have collapsed already. We're still viewing the form it took 14 millennia ago. The light we observe, the pulses we read, are rare-retarded views from the past. But imagine, for the sake of curiosity, that it did implode. What happens to the neighborhood of space around it? This is where things start getting tacky, when a pulsar implodes. As a black hole, it sacrifices the scaffolding that was maintaining its radiation beams aligned. The periodic pulse stops, but its surroundings don't immediately relax. The accretion disk, all that stuff still curving inward, continues to fuel it. But now, it's no longer fueling a pulsar. It's fueling a newborn black hole. This can temporarily produce something known as a relativistic jet, an highly energetic beam of particles and radiation emanating from the poles of the black hole, accelerated to almost light speed due to magnetic fields and rotational energy. If they just happen to be pointed in our general direction, even from 14,000 light years away, they can cause serious damage. That's not speculation. It's already occurred. Astronomers such as Adrian L. Mellitan, Brian C. Thomas, believe that a mass extinction event some 440 million years ago. The late Orvisian extinction could have been the result of a gamma-ray burst from an adjacent neutron star or black hole. It wouldn't have hit Earth like a bomb. Instead, it would have silently fried our ozone layer. The size of space is normally sufficient to get us out of harm's way. Nevertheless, the question remains, it can occur, and that is why the scientists continue to monitor. But let's reverse the question now. What if it didn't explode suddenly? What if it continued to expand gradually, drawing in more mass, piling on more pressure, inching ever closer to that tipping point, still spinning at 77 times pulse? Eventually, it becomes too late for even the spin to bail it out, and then, in an instant, the whole framework collapses. Certain models project this might release a very brief, highly rapid burst of gravitational waves, ripples in spacetime itself. Detectors, such as LIGO and Virgo, could capture it, providing us with a real-time record of a pulsar collapsing into a black hole. That would be a scientific first, but it would also be a cosmic testament. A message that one of Thephaster denser, more extreme stars in the galaxy just met its second demise, silently, without notice. And what takes its place? An unseen emptiness? A gravity well from which no light escapes. The beam that once pulsed through the galaxy like a clock gone. From a cosmic perspective, that's the end of the story. But for Mars, it's just getting started, because there's another type of neutron star that doesn't wait for collapse to be dangerous. It's one that doesn't have to spin at 700 times per second to wreak havoc. It's not faster, it's not more massive. It's merely magnetic. You'd expect that a star, which turns magnetars, when pulsars become even more terrifying, several 100 times a second, and is more massive than our sun, and is on the brink of implosion, would be through a case scenario. But nature, as ever, has a way of taking it further, because there is another type of neutron star out there. It doesn't rotate as quickly, doesn't have to. It doesn't require a companion star to consume. does not use beams of radiation to announce its presence. It warps thievery fabric of matter with something a lot more quiet and a lot more frightening. It's a magnetar. Now take all we know about neutron stars, the density, the gravity, the compactness, and superimpose a magnetic field so intense that it can actually rip atoms apart. Not just ionize them like normal radiation does, it's not just heat them up, it rips apart the structure of matter itself. A typical pulsar already has a magnetic field trillions of times stronger than Earth's, but magnetars crank that number up so high that it stops being relatable. The field of a magnetar can be over 1,000 trillion times stronger than Earth's. If you were anywhere near one, even thousands of kilometers away, your atoms would not cohere. The very chemistry of your booty would disintegrate under the pressure of magnetism. And it's not purely theoretical. We've seen their impact. In 2004, a magnetar called SG-1806-220, about 42,000 light-years from Earth in the constellation Sagittarius, produced a blast of gamma radiation so powerful that it overloaded sensors on several satellites. Despite originating from other half of the galaxy, for a brief moment, that magnetar outshone other X-ray sources in the sky put together. Had it been but 10 light-years nearer, then Earth would have been in trouble. And this is where it gets uneasy. Because unlike pulsars, which rotate and wane, slowly with time, magnetars are unstable. Their magnetic fields don't remain silent. They develop tension under the crust, and from time to time, the pressure gets too great. This produces what's referred to as a starquake. Think of a planet-sized body composed of ultra-dense neutron material cracking open like an agender. An excessive pressure. The crust shifts. The magnetic field realigns, sudden lion. The resulting energy release is size, so enormous it dwarfs our most powerful nuclear bombs, as firecrackers. These quakes release bursts of gamma and X-ray radiation that shoot out into space at light speed. And there's no warning, no foreplay, just a sudden flash. And the energy of 100,000 suns released in a split second. We're fortunate, by the way. The nearest known magnetar is around 8,000 light-years away. That's distant enough that even enormous flare wouldn't cause too much harm to Earth. But scientists have estimated TED if it went off within roughly 40 light-years. It would blow off our ozone layer, leaving the planet vulnerable to fatal ultraviolet radiation from the sun. And here's the catch. Magnetars don't last long. Their strong magnetic fields lose strength rapidly over a mere 10,000 to 100,000 years. A blink of an eye on cosmic timescales that makes the Munkaman. For every 1,000 neutron stars, only around 10 can be predicted to be magnetars. But even that is plenty. One is plenty. The magnetic field is so strong that even when the magnetar is not active, it's still influencing its surroundings. Any planet assuming they even exist would be continually immersed in high-energy radiation. And if a flare should occur during a close pass by a planet, the effect would be immediate sterilization. You don't need a supernova. You don't need a black hole. You just need a weakness in the crust and it's all over. That's what makes magnetars a new type of threat. They don't make themselves known with pulses. They don't build up in loudness over time. They're cosmic mines hanging in place. Silent, waiting, and if the conditions are just right, they explode. So, we've got neutron stars that rotate fast enough to provide artificial-like beacons. We've got magnetars that set the record for strongest magnetic fields in the known universe. And we've got at least one pulsar in our own galaxy that's teetering, on the brink of collapse. But let's consider the next question. What if one of them was nearer? What if one of these stars somehow wandered into our neighborhood? The math of doom. What if it were nearest to Earth? Up until now, every bit of it has seemed so far away. 1,000 light-years, 50,000 light-years. Even the nearest magnetars are thousands of light-years away, safely stashed behind ansia of space. And that's largely why most folks don't perceive the weight of it. Cosmic threat. When at sufficient distance doesn't feel tangible, but let's move it closer. Imagine one of these neutron stars. Whether it's a pulsar, a black widow, or an outright magnetar, somehow got kicked in our direction. Perhaps from a supernova explosion, perhaps a gravity nudge from some other star. Space is random, and neutron stars have been known to travel. In fact, some of them are traveling at over 1,500 kilometers per second, quicker than the galaxy can get away from them. Now, picture one of Thaw's stars, perhaps even PSRJO 9520607, somehow ending up in Jupiter's orbit. Let's say it pulled in and parked about 500 million miles from the Earth. That's still distant, right? Jupiter's out there. No problem. Think again, for starters, the gravity. Even at that distance, the gravitational force of a neutron star that large would begin messing with the orbits of planets in the vicinity. Jupiter, or Saturn, and even Uranus could have their orbits altered. Their orbits 2137 would over time destabilize, making the gravitational chaos seep inward towards Earth. And then there's the radiation. A pulsar such as J09520607 does not simply lie quietly. It spews twin beams of high-energy radiation from its magnetic poles, beams composed of X-rays, gamma rays, and charged particles. If Earth were in the way of ever known of those beams, we'd be in big trouble. Our magnetic field would provide some protection for a while, but the intensity would eventually overwhelm it. The ozone layer would be the first to disappear. Without it, solar ultravioletration would start sterilizing the surface, and it wouldn't stop there. I-themed constant bombardment by high-energy particles would begin destroying molecular bonds in the atmosphere. Satellites would fail, GPS would be lost, radio communications would fail, the night sky would be filled with unnatural glow, and the auroras, those whirling green lights at the poles, would blanket the whole planet, flashing incessantly like a signal. And if it's a magnetar rather than a pulsar, well, then rules change. A magnetar won't have to rotate at 700 times to create havoc. All it would take is closeness. If it were only a few thousand summon away, the mere power of its magnetic field would begin attracting the electrons in the atoms that constitute your body. You wouldn't even notice. Your body's very structure would unravel. It's not due to heat, not due to radiation, pure raw magnetic force. And if you were observing from a distance, let's say from the moon, the sight would not be much different. The Earth would begin to distort, not all at once, but gradually. Tides would get out of control. Crust could shift. Volcanoes would stir from slumber as pressure beneath the surface accumulates. Earthquakes would spread across continents as gravitational stresses build. Ultimately, the atmosphere itself, called to be stripped off, blasted into space by radiation pressure and magnetic disruption. The oceans would boil, then evaporate. The surface would be charred. Life would be extinguished. It's not in centuries or decades, but hours. And yet, to the neutron star, none of this will be perceptible. To a pulsar or a magnetar, Earth is merely another rock, a hunk of space junk that just got in the way. Our sun, not even a snack. If the neutron star was sufficiently massive, or continue drawing matter inward via an accretion disk, it might eventually collapse into a black hole within our own solar system. Then, gravity would reign supreme. Planetary orbits would shrink in. The sun itself would spiral into the event horizon and disappear. And that's the end of the story. Clearly, the chances of this occurring are very low. Neutron stars move quickly, yes, and are incredibly powerful. But space is huge. Most of them are moving across the galaxy alone. And though there are a few 100 million in the Milky Way, the likelihood of one stumbling into our backyard is less than winning the lottery each day for the next century. But that isn't the issue. The issue is, these objects do exist. They're aerial, and they're not unusual. They're spread throughout the galaxy. Some rotating faster than any human technology ever constructed. Some radiating invisible beams of lethal radiation, some with magnetic fields powerful enough to annihilate planets without even touching them. And some of them mysteriously have planets of their own. Can these monsters have planets? After all that we've told you about neutron stars, the gravity, the The radiation, the magnetic fields that might rip atoms apart, we might expect that nothing would survive close by. Anything as fragile as a planet, certainly, and yet a few have, not many. Indeed, only about 0.5% of all known pulses have been found. To host planets, that's out of the thousands we've detected. But those rare exceptions raise a strange question. How can a planetary system survive around one of the most violent objects in the galaxy? Let's start with the basics. Most stars form planets from leftover material, the gas and dust swirling around them during their early life. Formed in the exact opposite way, from destruction. A massive supernova explosion wipes everything out, and what's left behind is a crushed core spinning like a blender with a magnetic field that could sterilize entire solar systems. So the original planet's gone, which means that if a pulsar has planets, they either formed after the supernova or they were somehow captured later. One of the best known is PSRB 1257 plus 12. Some 2,300 light-years from Earth. It was the first pulsar ever discovered to have planets around it. And, believe it or not, it was the first verified discovery of any exoplanets whatsoever back in 1992. This pulsar has 3 planets. All of them rocky, all of them larger than Earth. And what's unusual is that they travel in pretty stable orbits. Not normal circular orbits, like our own solar system, but extremely elliptical, meaning they swing inward and then outward as they go around. The gravitational conditions around Pulsar are so strong that even slight variations get magnified. So the fact that these planets remain intact and still orbiting is strange. I consider living on one. This wouldn't be like Earth. The skies wouldn't have sunlight or a blue atmosphere. They'd be black permanently. Your sky would flash regularly with bursts of radiation, depending on whether the pulse's beam crossed your location. Instead of sunlight warming the planet, you'd get occasional pulses of high-energy particles enough to sterilize any exposed surface. The only chance for life to have existed would be buried deep beneath miles of rock, perhaps under thick ice, perhaps in oceanic cavities deep beneath the surface. Some scientists believe these worlds could be constructed from supernova remains, material that did not escape into space, but returned inward and cooled over time into a dusty disk. Over millions of years, that material could have coalesced into rocky planets. Others believe that the planets could be remnants, shards of a companion star torn apart by the pulsar's gravity, akin to cosmic leftovers squeezed into orbit. There's also the idea that the planets were captured, rogue planets wandering aimlessly in space, captured by the pulsar's strong gravity. It is less likely, but not out of the question. Particularly if the Pulsar had a companion star that was torn asunder and left behind planet detritus. In spite of how they became what they are, these planets are survivors. They've endured radiation, magnetic storms, and gravitational turmoil, and still quietly circle one of the most hazardous objects in the universe. Another pulsar, PSRJ 2007 plus 3120, has at least 2 planets. Again, both several times larger than Earth. One orbits every 1.9 years, the other 3.6. And just like with B1257 plus 12, their trajectories are not smooth or gentle. They're stretched out, disorganized, and constantly changing, like a car attempting to drive during a hurricane. The strangest thing is that we have no idea how unusual this actually is. We've only found pulsar planets orbiting a few dozen neutron stars, but perhaps it's just because they're difficult to spot. I mean, we're reinventing to find miniature worlds around objects barely the length of a city on thousands of light-years off space. And there they are. If life ever did form on one of these worlds, it would have to be something we can't even conceive. It wouldn't simply have to endure extreme conditions. It would have to be constructed for radiation, for turmoil, for wild energy that can vaporize an atmosphere in minutes. Which brings us right back to Earth. We revolve around a peaceful Stabililo star. We'll have a weak magnetic field, a breathable air mass, liquid water on the ground. In all conceivable ways, our solar system is abnormally quiet. The fact that stars can even have planets just makes it more apparent how bizarre and fortunate our circumstances actually is. But let's come full circle now, because this entire Talibagan with a title, Our galaxy's most perilous star could blow up at any moment. And the question was straightforward. Should we care? Should we care? We've discussed, should we be worried? About stars that rotate faster than jet engines, compress matter tighter than atomic nuclei, and fire beams off radiation that might vaporize the face of a planet. We've examined pulsars devouring their partners, whole-end magnetars that might explode like lightning-filled eggs and blast radiation over light years. It's like a horror film, but this is what really is. No, we're not in danger. It's not an nth way. People typically imagine hazard. PSRJ 095200607. It's going to shrink into a black hole tomorrow and destroy us from the face of the Earth. Magnetars aren't floating around nearby, waiting to vaporize our atmosphere. These things exist, but they're also far away. That is what saves us. Space, it turns out, is still really, really big. The most deadly star in our galaxy could blow up, sure, but that at any moment in cosmic terms means tens of thousands of years, or more. And if something similar to that occurred, the radiation would travel just as long to get to us. So even if the collapse had already occurred, we'd never know. We'd be looking into the past, as always one. We look at stars. But that doesn't make these things unimportant. Pulsars, neutron stars, and magnetars aren't freak objects drifting in space. They're reminders that the universe doesn't operate on comfort. It operates on physics, on pressure and collapse, on spin and radiation, on gravity, pulling everything in until they can no longer keep their shape. These stars remind us what happens when things are pushed to absolutal and beyond. They tell a tale that's less about threat and more about scale. Because what we call normal, a peaceful star, a stable orbit, an atmosphere thought keeps us safe. That's the rule. The majority of the universe is tough, unkind, full of energy being unleashed in ways we can hardly comprehend by objects we'd never serve if being around. So, no, we aren't in direct peril. But yes, we should take a notice, because somewhere not too far from us, a star is spinning itself apart. Gaining mass, losing control, getting near the precipice, and when it goes, it won't warn. And if you're the type of person who likes to take comfort, and the stars, don't think that all of them are friendly.